Let's begin video number 2 of chapter 14 and 15, Organic Chemistry. Um, Here is the very well-known aromatic alcohol phenol. I just wanted to emphasize that you can see it or draw it in any of three ways. Either the double bonds can be in these positions or in these. They just kind of move around the ring. So that's why we sometimes draw it as a circle. So the phenol aromatic alcohol is also known as benzenol. That's the IUPAC name. I particularly don't like that name, but that's what the IUPAC group has decided is the best name for it. But I like calling it hydroxybenzene because the hydroxy to me isn't. I'm very familiar with that. That's an OH. The prefix hydroxy is another way of saying that. Just like we call OH minus the hydroxide ion. So they're similar notations or names. But anyway, phenol is an old name that is stuck. It's like we call it water. We don't call it dihydrogen monoxide. These are common names that have stuck over the decades, so we use them. Organic chemistry is a very hard topic. I had a hard time getting I think a C my first semester because there's just so much information to digest. For instance, if organic chemistry courses talk a lot about reactions, I'm going to try to keep that to a minimum. I just want to show you some general ideas or what you can do with these molecules. Phenol is what's called an intermediate, or it's a precursor to aspirin. Aspirin is a very well-known painkiller, probably the first headache medicine that we discovered about over 100 years ago. This is what organic chemistry is and why it's so complicated. But you can take a compound, add groups at positions, like put something here, a carboxylic acid group it's called, and then you can change this OH into this. So this is what makes organic chemistry so hard. It's how do you remember all this stuff? Well, believe it or not, there are logical ways and rules that we can follow to easily predict and understand how it goes from here to here to here. Again, we're not going to do that in this class. This is just meant to be a survey of all these different types of molecules. A typical question I might give you on a quiz would be, give you a molecule like this and say, pick out or circle the important functional groups. So you'd notice an aromatic ring, you'd notice what appears to be an alcohol, but actually the OH is connected to a carbonyl, which we're going to get into shortly. This is called a carboxylic acid group. This connection here is called an ester group. So again, learn all the different functional groups and how to recognize them in larger molecules. Let's talk a little bit about how what you can do with alcohols on a very basic level. Alcohols can be oxidized to the next class of compounds I'm going to talk about, aldehydes and ketones. A lot of times when we indicate that something's oxidized, we just put the element oxygen in brackets like this. But really all that's happening when you oxidize an alcohol is you remove two hydrogens. You'll notice the only difference between this structure and this structure is that two hydrogens have been removed from this one to go to here. That's why we call this an oxidation. Oxidation in the organic chemistry sense it can be expressed in two ways. It means remove hydrogen or add oxygen. Here we've removed hydrogen, so this is an oxidation. And notice that everything's connected the same except right at the end. I'm converting this alcohol group into an aldehyde. So that's another thing about organic chemistry. It's very useful. It's like a cookbook for chemicals. We have all these different tools at our disposal, all these different disposal. We can do all these different things with organic molecules and make all sorts of things. All the drugs that we take for granted have been synthesized in labs using these very same types of reactions. Secondary alcohol, now that was a primary alcohol. A primary alcohol is oxidized to an aldehyde. If you take a secondary alcohol, again, that's an alcohol where the OH is attached to a carbon that has two other carbons attached to it. If you draw that out, and by the way, these are all redox reactions. That means carbon is increasing in oxidation number, and something else is having its oxidation number decreased. Just like we talked earlier in the class about inorganic reactions that were redox reactions, like what goes on in a battery. These are the same types of reactions. It's movement of electrons. The carbon is losing electrons essentially, and in this case the chromium is picking them up. So these are redox reactions. This is an oxidation. A secondary alcohol is converted to a ketone. Notice a primary alcohol is converted to an aldehyde because this functional group that is created is at the end of the chain. That's called an aldehyde. When the carbonyl group is created in the middle of a chain, because the OH was here attached to two carbons, the carbonyl goes here, that's called a ketone. That's acetone, the very common solvent that we use to clean glassware in laboratories. But again, an oxidation of this involves a loss of two hydrogens, just like the previous example did. We use inorganic compounds like this. This is called potassium dichromate. We use these as oxidizing agents because they contain a metal, in this case chromium, in a very high oxidation state, +6. So it has the ability to accept electrons. So the chromium is accepting electrons from the carbon is releasing them, and carbon is being oxidized. It's losing 2 electrons. It's going from a 0 oxidation state to a +2 oxidation state. I want to show you how we do that at the end of a lot of these handouts. I'll go through how I can show you pretty easily how you can predict that. And that's a helpful thing to know, because you can recognize if something is an oxidation reaction or a reduction reaction in an organic chemistry sense. So to summarize, an oxidation is just removing hydrogen and increasing the number of bonds between a carbon and oxygen. Here you had a single bond, now you have a double bond. You can't really oxidize this any further. The only thing you could do would be to burn it, which would convert it into CO2 and water. So CO2, carbon dioxide gas, is the highest oxidized form of carbon. So if you burn any organic compound, you essentially get water and CO2. That's why in all those combustion reactions I've gone over in this class, they always give you CO2 and water, because that's as far as you can go with taking carbon up to a high oxidation state. Another class of compounds you saw earlier are called ethers. Now, I introduced them here because they're related to an alcohol. An alcohol is an ROH. So you can think of an ether, that's a carbon with an OH on it. So you can think of an ether as just taking this hydrogen and replacing it with another carbon. It's an oxygen with singly bonded to 2 other carbon groups. The R prime just means that it's a different carbon group than this one, or they can be the same. Ethers are generally weakly polar molecules because they have an oxygen, so they do have an electronegative element in them, so they can interact with water a little bit. So the smaller ethers are slightly water soluble, but as you get the R groups to be anywhere between 3 or 4 and 5 carbons, or anything larger than that, they are pretty insoluble in water. But I wanted to just go over how you name ethers. So you should be able to recognize an ether. So you're looking for carbon groups of any length attached to an oxygen in the middle. So the oxygen is kind of like a bridge between the carbon groups. These are very volatile. They have low boiling points relative to to alcohols. So for instance, diethyl ether is a very common solvent we use in organic chemistry lab because it's very volatile. It dissolves a lot of things, so we use it to clean glassware like we use acetone for. But the problem with ether is it has a boiling point that isn't much above room temperature. The boiling point of ether is 35 degrees Celsius. That's just a hot summer day, a very hot summer day, but that isn't much above room temperature, so this stuff evaporates super quick. It has the ability to form peroxides, which are explosive, so we like to stay away from this stuff in laboratories. But notice how we named it. We don't stay away from it completely, I should say, but you have to be careful with this stuff. But this is diethyl ether. The way you name an ether is you just tell us what's bonded to the oxygen. In this case, 2 ethyl groups, so the diethyl, and the space, and then ether. Naming ethers that have the same groups attached are easy. You just put the di, because there's only going to always be 2, and then what you name it, what it's based off of. That's methane becomes methyl, ethane becomes ethyl. This is a gas at room temperature. The boiling point of this stuff is less than 20 degrees C. I don't know what it is, but it's a gas at room temperature because it's smaller than this one. As the carbons get longer, they liquefy because of the stronger forces between the larger molecules. What happens if you have an ether that has two different groups attached to the oxygen? Here you have an ethyl group and a propyl group. It was very easy to name. You just alphabetize the different groups, so E comes before P. This is ethyl, propyl, ether, and it's usually written as three different words. So keep that in mind. There's spaces intentionally put there that they are not written as one word, but that's the common name for an ether. The IUPAC name for an ether looks a little confusing. How did they come up with 1-ethoxypropane? Well, they said, okay, the longest chain of carbons that contains the important functional group, the oxygen in this case, is 3. So that's 3 carbons is propane. And then you say, okay, so where's the ether group relative to this longest chain? Well, it's at the first carbon. So we call it 1. At the 1 position, you have this. But how do we name that as an ether? We came up with the name ethoxy. This is ethoxy because it's an ethane or ethyl group with an oxygen on it. So you'd combine those two, ethyl and oxygen, and you get ethoxy. So that's how they came up with the IUPAC name, 1-ethoxypropane. At the 1 position, there's an ethoxy group. If you have a CH3O, we call that methoxy. That's another very common attachment or substituent. This is called, I hope you can see I think you can see that pen. It's not a felt tip pen, it's just a fine point pen, but that's called the methoxy group. So again, this is a language we're learning, so these are new words for you to learn, so to speak. These aren't super common, but they do come up occasionally. Ethers have very low boiling points and they're very volatile, as I've said. So now let's go to the rest of the compounds we'll talk about in these videos, at least until we get to the very last one, which is amines. All these following functional groups or types of compounds have this carbonyl group in them, the C double bond O. So let me just go over some of the characteristics of the carbonyl containing compounds. This word I'm saying, if you can't understand in the video, is carbonyl, spelled C-A-R-B-O-N-Y-L. That's this specific group here, this C double bond O. It's a very important type of bond. It's a polar bond. Aldehydes and ketones are similar. They have a series of carbons attached to this group, C double bond O. This is a way we write this is the condensed structural formula for an aldehyde. The aldehyde's always at the end of a chain because it has a hydrogen attached to it. That's what makes it an aldehyde. So that makes naming aldehydes very easy because there's no other position where this functional group could be. Ketones, the C double bond O, can be anywhere in the chain, so you have to use a number in the naming of a ketone, but you don't have to in an aldehyde if it's just a straight chain. The condensed structural formula for a ketone looks a little strange. It's a carbon group, and then this is the carbon of the carbonyl group, and then we put the oxygen in parentheses, because if we didn't, it would look like it's an ether. With an oxygen trapped between 2 carbons. So to distinguish that this is a ketone, the convention is to put it in parentheses to imply that this is this group here, the carbonyl group. The simplest aldehyde is formaldehyde, 1 carbon, and it's got a hydrogen here and a hydrogen here. So it's not a ketone because ketones, it looks kind of like a ketone, but if it has C double bond OH at the end, it qualifies as an aldehyde. This stuff is toxic. The IUPAC name for an aldehyde takes the parent name of the hydrocarbon that it's based on. So this is just 1 carbon long, so that's methane. And so they drop the E of methane and they add the suffix Al. So just like we added the suffix OL, all, for alcohols, we add the suffix Al for aldehydes. So it's a very similar sort of naming system for these 2 different types of compounds. Aldehydes are much more volatile than alcohols because aldehydes do not have the ability to hydrogen bond with themselves because they don't have an OH. They have an oxygen, just like ketones, so they can dissolve a little bit in water, but not once the carbon chains get longer than about 4 or 5. That pretty much goes for all these different types of functional groups as far as their solubility in water is concerned. The simplest ketone is you have to have 3 carbons in a row before you can get a ketone, because a ketone by definition is the carbonyl is attached to two different carbons. So this is the only possible, this is the smallest ketone you can get, and this is the acetone, which is also known as propanone. So I'll give you a few examples and a bit of how to name these as well. This stuff is very good in laboratories for cleaning glassware. It's weakly polar, somewhat polar, so it dissolves a lot of compounds. And so we use it in every organic chemistry lab to clean glassware. Very useful stuff, relatively cheap to make. Problem is it's got a pretty low boiling point, so it is somewhat flammable. You have to be careful with that. The main feature, again, as I said, is this presence of this carbonyl group. So you'll see this group a lot in all these functional groups coming up. Aldehydes, ketones, carboxylic acids, esters. They all have this, this carbonyl group, and it's polarized, as I've said before, with the carbon being partially positive and the oxygen being partially negative. So that means that influences a lot about the, that's a polar bond, so it creates a polar molecule when this is present. And it also influences the reactivity of these molecules, which we're not going to go into really. But that's a key to why these things are useful as intermediates to make other molecules, because of the presence of this specific bond, this carbonyl bond. Relative to alkanes, I kind of got erased there. That's supposed to say, that's an A. Relative to alkanes of the same size, aldehydes and ketones have higher boiling points because they do have the presence of this polar group. So they are somewhat weakly attracted to themselves because of the polar bond. That's a dipole-dipole force. That is not a hydrogen bond, though. It's a dipole-dipole attraction. So it's not as strong as a hydrogen bond. For that reason, aldehydes and ketones don't generally have as high a boiling point as alcohols of the same size. So how do we name these alcohols? What do you think we do for that? Well, it's similar to how we name the alcohols. We look for the longest chain of carbons that contains the functional group. So again, I already had this up on the previous slide, but formaldehyde, the simplest aldehyde, that's the common name. It comes from formic acid. Formic acid has one carbon, contains the same carbonyl group, but this is a carboxylic acid. The next group coming up after ketones, I believe, and this is a more highly oxidized form of an aldehyde because it has more oxygens. But nevertheless, aldehydes are named from their carboxylic acid parent. So this has one carbon called formic acid. That's the common name, so it's formaldehyde. You just put the word aldehyde at the end. But the IUPAC name is based on one carbon methanol, or methyl, as we've done with the other functional groups. So you take methane, you drop the E and add the Al, as I've said before. That's a more acceptable name in the modern chemistry terms. Let's look at an aldehyde that has 4 carbons long. It comes from the parent carboxylic acid that has the same number of carbons, 4 carbons, is called butyric acid. And so the name of the aldehyde, if you convert this to an aldehyde, which if you look carefully just means take away an oxygen, that's all you're doing, you get an aldehyde, but the name is based on that prefix, butyric, and then you just drop the IC and add the word aldehyde. The IUPAC name for this is butanal. Again, 4 carbons long, butane, drop the E, add the Al. So again, simple aldehydes like this that don't have any substituents on them, you don't need a number in the name as well, because we know that the aldehyde functional group has to be at the end of the chain. By definition, that's what an aldehyde is. Naming ketones, you have to use a number depending on how long the chain is. Now, the simplest ketone, just like I had up earlier, is acetone. You don't need a number here because this is the only place the carbonyl group can be. It can't be at the end because then it wouldn't be a ketone. So it's in the middle. So we call it it's based on 3 carbons, propane. But notice now, since it's a ketone, we give it the ONE suffix. So you'll notice that, you'll see that a lot. If it's an aldehyde, we give it the AL ending because that's the first few letters of the type of compound it is. A ketone, we take the ONE of the the class of compound. And we put it at the end, the ONE suffix, just like we did here with the name here, aldehyde. So, but a more common name for this is dimethyl ketone. That's not really used very much. The IUPAC names for ketones is more common. Now, if you get a ketone that is a little bit longer, now we have 5 carbons long that contains the carbonyl group. So now we do have to use a number because this could be here, here, or here. If it's here, it actually is the same compound as this. Just flip this one over. So the IUPAC name is at the second position. There's a ketone, and it's 5 carbons long, 2-pentanone. The preferred IUPAC name, the more modern name is I'm not a big fan of, but they take this, they take the parent hydrocarbon name pentane, and then they put the 2, the position where the ketone is, they put it near the end, separated by dashes, and then put the ONE suffix to imply that it's a ketone. I prefer this way myself, but either way is acceptable. By the way, a carbonyl group, so let me see if I have, I think I made a ketone. This is the structure of acetone. So we learned earlier in this class that a carbon, for instance this one, that has 4 bonds around it, but it has, I don't think we talked about hybridization, but a ketone has a carbon that is flat. This is a trigonoplanar molecule. So this molecule is flat. If you look at it end on, this is flat, meaning the carbons are all kind of in the same plane. But this is the structure of acetone. This is a 120-degree angle. So this is common for even in aldehydes. You'd have the same angle. This is a 120-degree angle. This is a 120-degree angle. This angle here is 120 degrees. That I know we draw these molecules on a piece of paper, but they are real 3-dimensional molecules. So even something as simple as acetone looks a little bit complicated when you actually look at it. But this is that carbonyl group I'm talking about, the C double bond O. Here, with this sort of molecular model, unfortunately, we're not in class, so it would be, we like students to work with these models to kind of get a real picture of what molecules look like. So you'll have to kind of just use your imagination to see what this is in 3 dimensions. But in the video, I'm sure it will definitely help you more than just me telling you what it looks like or looking at a textbook. But again, you'll see that aldehyde, that carbonyl group in a lot of places. This is a carboxylic acid, and it looks like a ketone, but because it has that same carbonyl group. So again, it's flat at that point. It's flat at this point, and its angles of 120 degrees. So a carboxylic acid has the same sort of piece, the carbonyl group, but now it has an OH at the end. So different chemical type of reactions this can go through. So you can also have ketones that are cyclic. This is based on cyclobutane, so we name this one cyclobutanone. No number is needed. If we put something on the ring, like if we put something here, I'd have to say that that's the 2 position. So for instance, if I put a methyl group there, that would be called 2-methyl cyclobutanone. Pretty straightforward stuff. I hope you are seeing that this is pretty logical stuff, hopefully not too complicated. Let's go through some more examples just to reinforce these rules, and then I will end this video and then continue on with the next class of molecules called carboxylic acids. So here's naming an aldehyde and a ketone that are slightly more complicated. So pretend you don't see that name. I give you this structure, or if I give you the name, you should be able to write the structure. But how did we come up with this name? So I didn't draw in all the hydrogens, so let me just do that now. There's an H there, an H there, an H there. And you can see why I prefer drawing in or using the line drawings, because they're so quick to write. But you guys, it probably is a good idea to write molecules like this, to draw molecules like this and like this, just for practice to see how everything's connected together. If you're comfortable doing it this way and fully understand it, it's up to you. You can just have at it and draw it that way. I'll leave that up to you. But again, how do we name this compound? Very logical again. Here's the functional group. So it's key that you can recognize that that this is a aldehyde. It contains some halogens, bromine and iodine. So some people think, well, maybe that's it's called an alkyl halide. It's a carbon with some halides. Nope. This takes priority. If you have two different functional groups or two different classes of compounds within the same structure, one of them has to take priority. And this takes priority in this case. So this is named as an aldehyde. So notice the Al ending on the name of the compound. So the longest chain that contains that is here. Do we number it from here or there? Obviously we number it from here because that takes priority. That's position 1. That's carbon 1, 2, 3, 4, 5, 6, 7. So at the third carbon, I have a 1, 2, 3. I have an iodine, and at the 1, 2, 3, 4, 5, I have a bromo. So this, and then notice I alphabetize them. You've seen that a lot. The numbers, you don't care if the numbers go from low to high. You care that the letters of the substituents are alphabetized. So B comes before I. And so this is at the 5th position, there's a bromine. 3rd position, there's an iodine. Notice we drop the INE and call it bromo iodo. So again, practice that, remembering that the halogens are named with an O ending, chloro, bromo, iodo, fluoro. And then again, just like we named all the other different types of compounds, you give the position that is at, separated with a dash between the number and the letter. And no commas needed in this compound because there's not more than one of anything at a particular carbon. And then we don't put a dash here. Once we've named all the substituents, the bromine and the iodine, no space, just write the word heptane for 7 with the Al ending. And then again, it's a good practice to draw this line drawing from here to here. So 1, 2, 3, 4, 5, 6, 7. Here's how a aldehyde looks on a line drawing. Notice I have to put the hydrogen in. So even on a line drawing, like if you drew the line drawing of heptane, it would be 1, 2, 3, 4, 5, 6, 7. That would be C7H16. That's good enough for alkane because there's no other groups. That we know that those are carbons and hydrogen. But now we're in slightly more complicated molecules, so we have to indicate that the hydrogens if I didn't put that there, you would think that's a carbon. So to specify that it is a hydrogen, I have to write it in. Don't forget that. And then I have to put that that's an oxygen. So anything besides a carbon, you have to put, you have to actually explicitly write out in a line drawing. So that's about as simple as I can write that compound. Here is a ketone example, slightly more complicated. I haven't drawn in all the hydrogens, so there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So the molecular formula of this compound, I don't like that small pen on these videos. It doesn't look, the molecular formula of this compound would be C, 1, 2, 3, 4, 5, 6, 7, 8, 9, C9, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I did that right. H12. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, C9, H12. And then it's we generally put the oxygen next, and then you put anything left over, bromine, at the end. So that would be the molecular formula if I did that right. If I made a mistake, I apologize, but that's how you write the molecular formula. Again, molecular formulas are not that useful. They don't tell us the structure of anything. They just tell us what the ingredients of this molecule are. There's probably, I don't know, 10 different ways you could combine a bromine and an ethyl group in this molecule. All right, so how do we name it? We say, well, I recognize that it's a ketone. It has this carbonyl group that's in the middle of a carbon chain. So it's not an aldehyde because that's at the end of a chain. Notice it's at the end with a hydrogen. Here we have this, it looks similar, but you gotta look carefully. It has the same C double bond O, but now it's in between two carbons. So it's a ketone, so it ends in O-N-E, not A-L. That'll take a little review or practice for you. If you read the textbook, you'll see many examples of these. I'm just going through a few here. There's not time to go through all the ones. So go through some of the textbook examples for practice. All right, so this is carbon 1 because that will give the carbonyl containing carbon the lowest number. 1, 2, 3, 4, 5, 6, 7. So it's heptane, and it's a ketone. So drop the E of heptane and add O-N-E just like we've done before. And then at the second position is where my ketone is. And then at the fourth position, I have an ethyl group. So actually, that's wrong. I missed those hydrogens. Let's redo that. Apologize for that. But at the fourth position, there's an ethyl. And then at the fifth position, there's a bromine. So you can see I've numbered the chain here. So again, this is 5 bromo, 4 ethyl, 2 heptanone. So really, there's the molecular formula of that is C9, should be H. Let's see, let's count them again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes, that makes sense. H17OBr. All right, so now this is why I like line drawings. I just instantly can draw this and see that this is this compound. Here's my 7. 1, 2, 3, 4, 5, 6, 7. And here's my ethyl group, and here's my bromo group. Notice in this particular drawing, the ethyl is pointing downward. It doesn't matter. These are three-dimensional. They can flip. If I flip this over 180 degrees, I get this. So remember that. You can look at these from many, many different ways. I think we're at a little over 30 minutes on this video as well. So I will end video number 2, and we'll start up video number 3 with discussion of carboxylic acids.